Look at the first ever image of the Andromeda Galaxy, captured by astrophotography pioneer Isaac Roberts in distant 1888. What do you see? If you were an astronomer of that era, convinced that the Milky Way was the entire universe, you would likely have seen only a fuzzy gas cloud. Perhaps it would have appeared as a young star system, just beginning to form. In any case, this object had to be part of the Milky Way, because beyond its boundaries, it was then believed, nothing existed. However, there were brave souls who dared to question this established worldview. They put forth a daring hypothesis. What if this was not just a cloud of gas, but an entire other galaxy, a separate, island universe, similar to our own Milky Way? These ideas sparked heated debates, most notably the 1920 discussion between astronomers Harlow Shapley and Heber Curtis at the National Museum of Natural History in Washington. These historic debates decided the fate of the so-called spiral nebulae. Shapley insisted they were within the Milky Way and simply too small to be anything more. Curtis, however, argued that far more new stars were appearing in Andromeda than in other parts of the Milky Way, which could hardly be a coincidence. Moreover, he noted that the dark lanes in Andromeda were very similar to the dust clouds in our own galaxy. He supported the island universes idea, tracing back to Immanuel Kant, who also hypothesized that spiral nebulae were beyond the Milky Way. The resolution to this captivating story came when young Edwin Hubble measured the distance to Cepheids, variable stars in Andromeda's disk, obtaining a staggering figure, over 1 million light-years. He announced this discovery at an astronomers' meeting in 1925. This sparked widespread excitement, as it was the largest distance ever measured, and it meant that Andromeda was a star system entirely separate from the Milky Way and in many ways similar to it. Simple observation of the changing brightness of stars, also performed for other nebulae, showed that the universe was much larger than the Milky Way. It was then that the true universe was born in our consciousness, a universe of galaxies. It is difficult to ascertain who first discovered Andromeda, as it is visible to the naked eye, especially in an era without light pollution. Therefore, many observed and catalogued it. The first mention is attributed to the Persian astronomer Abd al-Rahman al-Sufi, who in 964 AD described it as a small cloud, in his Book of Fixed Stars. Charles Messier, in 1764, included Andromeda in his famous catalogue of objects to avoid when searching for comets. In Messier's catalogue, it was assigned number 31, hence it is often referred to as M31 in astronomy. It received its name in honor of the Andromeda constellation, where it can be found in the sky. So, M31 is a large spiral galaxy, very similar to the Milky Way, but somewhat larger in size. It is our closest neighbor among the so-called normal galaxies that fit into Hubble's classification. Although, given the enormous number of irregular galaxies, perhaps the notion of normality should be reconsidered. Hubble's initial distance estimate, just over 1 million light-years, was revised after the discovery of a new type of Cepheid. Modern estimates for the distance between the two main galaxies of the local group are about 2.5 million light-years, which is quite small by galactic standards. To observers from outside the local group, Andromeda and the Milky Way would likely appear as a binary galactic system, were it not for the Triangulum Galaxy, a third spiral, significantly smaller but still substantial. Thanks to its relative proximity, Andromeda occupies a significant area of the sky. Unfortunately, our eyes are not the best telescopes, so only its core can be seen with the naked eye. But with a telescope and long exposure, the fainter outer regions of the galaxy become visible. In images, Andromeda can span over 2 degrees of the sky, which is 4 times the apparent size of the Moon, and this is still not the entire galaxy. Such structures do not have sharp boundaries. The diameter of M31's disk is estimated to be approximately 220,000 light-years, and the number of stars it contains could reach 1 trillion. This means that Andromeda might be 1.5 times larger than the Milky Way. However, these are only approximate estimates, as it is difficult to accurately determine the size of our own galaxy while being inside it. Determining the mass of cosmic objects like galaxies is a complex task that goes beyond the simple application of Newton's and Kepler's laws. These laws allow us to calculate the mass of planets and satellites based on their orbital speed and distance from the central body. However, when astronomers tried to apply this approach to galaxies, they encountered unexpected results. At first glance, it seemed that the majority of a galaxy's mass should be concentrated near its core. Consequently, stars closer to the center should move faster than those located at the periphery, similar to planets in the solar system. But in the 1970s, Vera Rubin and Kent Ford, studying the Andromeda galaxy, M31, discovered that this assumption was not true. Stars on the outskirts of Andromeda moved at almost the same speed as stars near its center. This indicated that the visible mass in the galaxy's center was insufficient to explain such motion. Moreover, the star's speeds were so high that the galaxy should have torn apart due to centrifugal force. Rubin's research and that of her colleagues, spanning over 20 spiral galaxies, confirmed this conclusion. The galaxy rotation curves did not show the expected decrease in speed with increasing distance from the core. This became strong evidence for the existence of so-called hidden mass, or dark matter, which fills the universe and interacts with ordinary matter only gravitationally. Dark matter does not emit electromagnetic waves, making it invisible to modern telescopes. Thus, weighing galaxies turned out to be a much more complex task than, for example, determining the mass of Uranus. To account for the hidden mass surrounding galaxies, new measurement methods were required. Scientists attempted to estimate galaxy masses based on the dynamics of gas movement in their disks and at their outskirts, and they also measured the velocities of globular star clusters surrounding Andromeda and the Milky Way. Studying satellite galaxies, whose number is constantly growing, appeared to be the most promising direction. Estimating their orbital speeds allowed for the determination of the mass around which they orbit. However, despite all efforts, the results of galaxy mass estimates obtained by different methods often differed by orders of magnitude. In 2018, astronomers reached a consensus that Andromeda and the Milky Way likely have similar masses, about 800 billion solar masses each. But already in 2019, data obtained by the Gaia spacecraft showed that the Milky Way's mass could reach 1.5 trillion solar masses. This was almost double the latest estimates for Andromeda's mass. If true, then Andromeda would not engulf our galaxy in the future. Instead, the Milky Way would engulf Andromeda. However, a new study based on the third Gaia data release was just published recently, and the new estimate for the Milky Way's mass is only about 200 billion solar masses, which is several times less than previous estimates. Thus, determining the mass of galaxies remains a complex and unresolved problem. Despite the difficulties in determining its mass, the Andromeda galaxy, M31, remains one of the most beautiful and studied objects in the night sky. It is classified as a barred spiral galaxy, just like the Milky Way. Even when viewed through a small telescope, its spiral structure and dark dust lanes can be seen, which are particularly clear in one region of the galaxy and less distinct in another. This is because part of the galactic disk is located behind the central bright region, called the bulge. Millions of faint old stars obscure the view, making the dust lanes less pronounced. In ultraviolet and infrared images of Andromeda, the spiral arms brightly dominate. This is because the hot young stars inhabiting the arms primarily emit high-energy photons in the ultraviolet part of the spectrum. When these photons heat the surrounding gas, it begins to radiate primarily in the infrared. The best and most detailed image of Andromeda was taken by the Hubble Space Telescope. This panorama, published in 2015, is the largest image from Hubble ever released. To create this panorama, which covers only a third of Andromeda's disk, the telescope had to change its position 411 times and perform over 7,000 exposures. This panorama, spanning about 61,000 light-years, depicts over 100 million individual stars and thousands of star clusters. On the left side of the panorama, the galactic bulge, densely populated predominantly by old, relatively cool stars, can be seen in detail. Further on, the panorama leads us through numerous lanes of stars and complex dark structures formed by dust, ending near the sparse outer disk, where young, bright stars outline a giant blue ring. Upon zooming in, numerous star clusters and areas of active star formation can be discerned. These clusters appear particularly bright in ultraviolet images from the Swift Space Telescope. At the very heart of the Andromeda Galaxy, in its birthplace, young and bright stars form a giant ring known as the Ring of Fire. It is here, in this cosmic necklace, that the main star formation activity in the Andromeda Galaxy is concentrated. But why here? One hypothesis suggests that the Ring of Fire is the result of Andromeda's continuous interaction with its satellite galaxies. The gravitational forces arising from these interactions compress gas clouds, triggering the process of new star formation. There is another hypothesis, which we will consider later. Notably, the largest star-forming region not only in M31 but in the entire local group of galaxies is NGC 206. Its dimensions are impressive, approximately 4,000 light-years across, and its stellar mass is estimated at 200,000 suns. This structure is classified as an OB association, home to over 3 million stars of spectral classes O and B. These are hot blue and blue-white giants, whose young age does not exceed 10 million years, mere infants compared to our Sun. Nevertheless, in terms of overall star formation, Andromeda is somewhat less active than the Milky Way. Our galaxy produces 3 to 5 solar masses per year, while M31 produces only 1 solar mass star. However, according to a 2011 study, both galaxies have already passed their peak activity in star formation. By comparing the color of the Milky Way and Andromeda with data from the Sloan Digital Sky Survey, scientists concluded that the fuel for further star formation in both galaxies is gradually depleting. Perhaps in 5 billion years, they will practically cease giving birth to new stars, and even with a future merger, which should lead to gas compression, the starbursts will only be brief. The authors of the study cleverly titled their work, "The Milky Way and M31's Midlife Crisis." One of the distinguishing features of galaxies like Andromeda and the Milky Way are their enormous star clusters, resembling individual galaxies themselves. We are talking about globular clusters, of which Andromeda has over 450, 3 times more than our galaxy. But it is important to remember that we observe the Milky Way from within its disk. Globular clusters, which are spherical in shape, contain hundreds of thousands, and sometimes millions, of stars. Notably, these stars are typically very old, in fact, the oldest not only in their galaxies but in the entire universe. These are second-generation stars, with low heavy element content, aged between 11 and 13 billion years. It is believed that globular clusters formed in the vast halos surrounding galaxies even before they took the form of spiral disks. However, the formation mechanism of these structures still remains one of the mysteries in galaxy evolution. The largest globular cluster in the local group, associated with Andromeda, orbits its core at a distance of 130,000 light-years. Mayall 2, also known as Globular 1, contains several million stars and is more than twice as massive as Omega Centauri, the Milky Way's largest cluster. The varying metallicity of Mayall 2's stellar population and its enormous mass suggests that it may be the core of one of the dwarf galaxies swallowed by Andromeda during its evolution. As in any spiral galaxy, the highest concentration of stars is observed near its core. In this image taken by the Hubble Space Telescope, an area about 8,000 light-years across is visible. Millions of stars surrounding the supermassive black hole at the center merge into a single bright source of light. The blue dots scattered throughout the image might give the impression that these are young and hot stars. However, in this case, these are so-called ultra-blue stars, aging sun-like stars that have prematurely shed their outer layers and exposed their scorching cores. Hubble captured them at their peak brightness, shortly before transforming into white dwarfs. The image was obtained using several filters, including ultraviolet, which explains their brightness. Metal-rich stars near the core shed their outer layers more efficiently, ejecting more matter than stars with lower metallicity. Therefore, they are much brighter in the ultraviolet range than, for example, the Sun will be in a few billion years when the same thing happens to it. Observations confirm this theory. The number of ultra-blue stars decreases with increasing distance from Andromeda's core, which corresponds to a decrease in stellar metallicity. But let's not rush to leave the core, as another surprising feature awaits us here. In the late 1980s, ground-based observations showed that the brightest part of M31's core was offset by several light-years from its presumed center. In 1991, Hubble revealed this mystery. It turned out that Andromeda's core has a more complex structure than previously thought. It is double. In the Hubble image, the true center is the fainter region, while the brighter one is located 5 light-years away. Within the fainter core, a supermassive black hole with a mass of over 100 million suns likely lurks. But what then is in the brighter part of the core? A very intriguing hypothesis suggests that the mysterious formation is a surviving fragment of a dwarf galaxy, once swallowed by M31 about 1 billion years ago. According to this version, the only thing remaining from the vanished galaxy was its bright core, continuing to orbit Andromeda's center. However, this theory has lost its former popularity, as the powerful gravitational field of the supermassive black hole hidden in M31's core should have torn the cluster apart. Computer models show that the swallowed galaxy's core would not have survived even a few 100,000 years before being destroyed and completely mixed with the dense stellar population of Andromeda's center. The only chance for this cluster to survive would be the presence of its own black hole at its center, but the distribution of stars does not indicate its presence. Today, most astronomers lean towards the view that the double nucleus is merely an optical illusion. In reality, it may be a ring of old red stars orbiting the core on highly elongated elliptical trajectories. Moving along such eccentric orbits, stars slow down at their most distant points, leading to their clustering in these areas, like a traffic jam, creating the appearance of a second nucleus. This concept developed further in 2021 when scientists demonstrated how gravitational wave emission, arising from the merger of supermassive black holes, can drive stars into long, eccentric orbits, creating the illusion of a second nucleus. In 2012, the Hubble Space Telescope re-examined this region and discovered that young, bright stars orbit the fainter core of Andromeda, marking the galaxy's true center. A similar pattern is observed in the center of the Milky Way. These blue stars are no older than 200 million years, and they could hardly have formed elsewhere, as their short lifespan would not have allowed them to migrate from the surroundings to the center. Consequently, they were likely born here, in the harsh conditions near the supermassive black hole, during a powerful starburst. It is surprising how stars can be born and survive in such extreme conditions, but a similar pattern is observed in our galaxy. For example, the star S2, closest to the Sagittarius A** black hole, is a blue-white giant of spectral class B, as are about 100 other stars nearby. It seems that a young, bright cluster near a black hole is a common feature of spiral galaxies. One possible explanation is that these stars are born directly in the accretion disk, where dust and gas rotate and compress, but there is no convincing evidence for this hypothesis yet. Andromeda's current appearance is the result of its long and turbulent history. It is a true cosmic predator that does not mind feasting on its smaller neighbors, such as M32 and M110. However, there is a theory that it encountered not only dwarf galaxies on its path. Perhaps just a couple of billion years ago, what we know today as Andromeda could have been 2 spiral galaxies. Astronomers find traces of a large-scale collision both in Andromeda's disk and on its outskirts. For example, it has a significantly larger and more massive galactic bulge than the Milky Way. Its faint halo, surrounding the galaxy's disk, is more diverse and contains several significant stellar streams. Some of these are truly enormous. One has even been named the Giant Stream, a tail of stars stretching towards the galactic disk. Furthermore, the ring of active star formation, known as the Ring of Fire, may be the result not only of tidal interactions with M32 but also of a much larger collision that occurred about 2 billion years ago and triggered a starburst. And perhaps most importantly, the dynamics of Andromeda's stars older than 2 billion years point to a major merger. In 2018, astronomers at the Paris Observatory attempted to put all the pieces of the puzzle together using a large-scale simulation on a powerful supercomputer. The results of their work, presented as an animation, currently best explain the observed properties of Andromeda. It turns out that 2 spiral galaxies could indeed have existed in the local group in the region of space where Andromeda is now located. The smaller of them had a mass of about 25 billion solar masses but was at least 4 times less massive than its companion, which can be considered Proto-Andromeda. As a result of a violent merger, completed approximately 2 to 3 billion years ago, Proto-Andromeda absorbed its neighbor, transforming it into the strange compact galaxy we know today as M32. This dwarf satellite of Andromeda may be just the remnant of a former large galaxy that once graced our local group. Indeed, M32, although it looks like a miniature version of a typical elliptical galaxy, is only so at first glance. In the ultraviolet range, it is quite bright because it contains many young hot stars, which is uncharacteristic of typical elliptical galaxies. Thus, it may represent the remnant of a larger spiral galaxy. The simulation conducted by the scientists reproduces Andromeda in its familiar form quite accurately. Moreover, it accurately reproduces the giant stream, which may be a trace of that very large-scale merger. In fact, it represents a large mass of stars that are still being drawn towards the galaxy's disk as the final stage of the past merger. Andromeda's brightest satellite, known as M110, also shows signs of interaction with its host galaxy. This object is a dwarf elliptical galaxy, containing about 10 billion stars and at least 8 globular clusters. Notably, M110 cannot be called a dead galaxy, as populations of young blue stars and dust clouds have been detected within it, indicating active star formation processes. In addition to M32 and M110, about 24 other dwarf satellite galaxies orbit Andromeda. In 2013, as part of the large-scale Pan-Andromeda Archaeological Survey, astronomers studied the structure of M31 and the distribution of its satellites. One unexpected discovery was that at least 15 of these satellite galaxies do not orbit Andromeda's disk on random trajectories. Instead, they appear to be concentrated in a flat, thin disk, forming a disk of satellites. A similar phenomenon is observed with the Milky Way's dwarf satellites, where a disk of satellites was first noticed 4 decades ago. However, such a distribution of galaxies is difficult to explain not only by existing models of their formation but also within the framework of modern cosmology. Satellite disks remain a subject of debate, and some studies question their existence, criticizing observational methods or data interpretation. In any case, scientists still have much to learn about galaxies and their evolution. Nevertheless, few doubt the impending collision of M31 and the Milky Way. Andromeda, it seems, has already experienced something similar, while the Milky Way will encounter it for the first time. Although estimates for the timing of this event vary from 5 to 6 billion years, it can be assumed that the merger has already begun. The circumgalactic space of Andromeda and the Milky Way is not empty. Besides stellar streams, a significant amount of hot ionized gas and dark matter is concentrated here. However, it is not yet clear how far these components extend from the galaxy's disks. The stellar halo represents a nearly spherical volume of stars and globular clusters surrounding the galaxy. These regions contain only about 1% of the galaxy's stellar mass, and these stars are relatively old and cool. Because of this, the halo is faint and difficult to observe. However, there is also a giant bubble of diffuse gas, known as the galactic corona, which is practically invisible. In 2020, a group of scientists, using the Hubble Space Telescope, managed to create a map of the distribution of this ionized gas, or plasma. Since the plasma halo is difficult to observe directly, the best way to determine its density is by observing light passing through it from distant sources. At certain wavelengths, this light should be absorbed by the gas envelope. By studying the light from more than 4 dozen quasars, scientists concluded that the plasma halo extends approximately 1.3 million light-years from Andromeda's disk, which is about half the distance to our galaxy. The halo is so enormous that it would appear 3 times the width of the Big Dipper or 100 times the size of the moon in the sky if it could be seen with the naked eye. Since we are inside our galaxy's disk, it is difficult for scientists to determine how far into space the Milky Way's halo extends. If M31 and our galaxy are indeed similar, they may also have similar gaseous halos. In that case, it can be argued that both galaxies have already begun to collide or are on the verge of merging their halos. there is no need to discuss the consequences of this collision for humanity. Even if our civilization can survive long enough to witness the formation of Andromeda, this event is unlikely to have any significant impact on us, other than aesthetic pleasure. It should be remembered that even large structures like galaxies are mostly empty space, and the collision of individual stars during a galactic merger is unlikely. Instead, it is worth considering that when we look at Andromeda, we are seeing light that is 2.5 million years old. When those photons left their galaxy, humans on Earth looked very different. But how important are these photons to us today? Through our telescopes, we learn that the universe is far vaster than the Milky Way. And this is certainly not the end of the story. Andromeda's role in our understanding of the universe and our place within it is far from complete.